So good afternoon. My name is Dr. Richardson. This is lecture 2 of the course, An Introduction to Linear Algebra using Python. Again, you can reach me at my email address, srichards22@comcast.net. And just some organizational details. Please remember that learning is not a passive activity, so please take notes. You will get nothing out of this course by just sitting and watching me write notes. You need to write them in real time, either if you're doing it live or even if you're looking at the video clip. Please take notes, just don't watch. Problem sets. There are weekly problem sets, and you need to do them. Taking the course without doing the problem sets is a surefire way to basically learn nothing. So just looking at the ideas, but having no experience in going over and applying the concepts is not the way to go. And again, the problem sets have two parts. There are problems that are analytical, that are meant for you to do by hand. And then there are a set of Python exercises. They're really lab exercises that you can do, and they're self-contained. I encourage you to ask questions. I'm available through my email address. And I promise to get back to you within 24 hours if you have problems or questions with any lecture material, problem sets, or even the solutions. And it's also useful to bring a ruler with you in writing the notes and actually doing some of the problems. So lecture problem set 1 is available, problems and the solution key is available, and problem set 2 is also available. I ask you to take probably, in terms of your schedule, about a week to work on the problem set, but don't just simply ignore the problem set and look at the solution key and work backwards. That's not the right strategy to employ. Okay, so last time we were looking at a way called the method of cofactors and minors. And this method is a very easy way of calculating determinants. So this method answers the question, how do you find the determinant of a matrix? So remember that the goal in this first couple of lectures is to solve a system of linear equations. And you want to solve the system of linear equations simultaneously. In order to do that, we showed last lecture that Cramers Rule is an ideal way of sitting down and accomplishing this task. The problem, I wouldn't say it's a problem, but we came up with the realization that in order to use Cramers Rule, you need to be able to evaluate a determinant of a matrix. And in fact, we looked at 2x2 determinants and 3x3 determinants. I will argue and say more about this later. If you want to look at matrices of higher order, in other words, matrices that have 4 rows and 4 columns, or 5 rows and 5 columns, then Cramers Rule is going to get more difficult to use because the determinants are going to get larger. But that's where, in principle, the method of cofactors and minors comes to our rescue. So we looked at an example that I'm going to return to of a coefficient matrix A. This was a matrix that had 3 rows and 3 columns. So in fact, it had order 3. When you say a matrix has order 3, it means that it's a matrix that has 3 rows and 3 columns. And if you want to apply Cramers Rule, or rather the method of cofactors and minors, you have to expand the determinant of A across some part of the matrix. And what we did last time, we expanded it across row 1. And we got an answer. Now I want to do the same problem, but I want to use cofactors and minors to expand across not row 1, but row 2 of the coefficient matrix. So how do I do that? Well, the method of cofactors and minors says that if I'm expanding across row 2, I have A sub 2, 1, the matrix element A sub 2, 1, A sub 2, 2, and A sub 2, 3. And each one of those matrix elements gets multiplied by a creature which has a capital letter, the alphabet, same set of subscripts. These matrix elements are coefficients, or just numbers. But these capital letters are what we define as cofactors. So the way you tell your audience that you're dealing with a cofactor is you write it as a capital. It's a symbol written with a capital letter. So I have 3 terms to evaluate, 1, 2, and 3. And similar to the example we looked at last lecture, we'll go through this one step at a time. So A sub 2, 1 by inspection for this example is just 0. The cofactor A sub 2, 1 is by definition minus 1 raised to the 2 plus 1 power times the minor m sub 2, 1. And remember, the minor is the determinant of the matrix that you get when you eliminate from the coefficient matrix the second row and the first column. So I'll just write it here as a reminder. Here's A. And if I eliminate the second row and the first column, then I'm left with a smaller matrix of order 2, and the minor M21 is just the determinant of that. And that's easy to evaluate. That's just minus 1 times 1 minus 1 times 2. And actually, this is a minus 2. So then this is a positive sign. So this cofactor, this minor is 1. So again, it's always useful when you do use the method of cofactors and minors to take your time, because there are 2 places where you can make mistakes. We saw one example. You can make a mistake with transcription. In other words, you turn a minus sign into a positive sign when you shouldn't. And the other mistake you can make is in terms of the arithmetic. So it's always a good idea to spell this whole thing out. So we can put all this together. The first term is simply 0 times minus 1 raised to 3 times 1. And so there's no contribution from the first term. Second term in this expansion, A sub 2, 2, by inspection is just 3. So the cofactor A sub 2, 3, or A sub 2, 2, is in fact minus 1. This is just the definition of the cofactor, raised to the 2 plus 2 power times the minor 2, 2, m sub 2, 2. If you go back to the original coefficient matrix, you can discern that the minor is simply this determinant, which again, I'll do it the long way, vanishes. So that second term has no contribution at all either, because it's 3 times minus 1 raised to the 2 plus 2 power times 0, and all that becomes 0. So 2 down, 2 to go, or 1 to go. Our third and final term, when we did the expansion of the determinant across the second row, we need to look at what a sub 2, 3 is. By inspection, it's just -1. So we need the cofactor. The cofactor is -1 raised to the 2 plus 3 power times the minor m sub 2, 3. And again, go back to the original coefficient matrix, kill the second row, the third column. You're left with a smaller matrix of order 2, and take her determinant. And that's exactly what you should get here. So that's 2 times -2 minus -1 times 2. So that should give you -2. So there is a contribution from the third and final term in our expansion. It is -1, that's just a sub 2, 3, times -1 to the 2 plus 3 power times -2. And you have 3 minus signs. They all multiply each other, so you get a final result of -2. So your final answer, let's put this in red, to this problem is going to be that the first term vanishes, the second term vanishes, and the third term is still there. And the beautiful thing is, this is exactly the same answer that we got last time. Only now we were doing the expansion across the second row of the coefficient matrix. Before, we were doing the expansion over the first row. We get the same answer. So let's practice makes perfect. Let's go through another example.
Excuse me, Dr. Richardson.
Yes.
I think we forgot to do the live captioning.
Hold on, let me. According to the full transcript, it's captioning, Tina. I'm looking at the full transcript now on the screen. So I can go in and look at the full transcript. It is captioning. Do you see that? I don't know if you can see this as a non-host, but it is captioning. Tina?
Okay. I see it now. It wasn't.
It's working. It's been working at my end.
Okay. All right.
All right. So where were we? All right. So this gives you the same answer that we got before. All right. So now let's repeat this problem. And let us do the expansion. So let us expand. Let us expand the coefficient matrix, or it really expand the determinant of the coefficient matrix. And let's do it about the third column of A. So again, I got to write down what the coefficient matrix is for the problem. It's a matrix of order 3, has 3 rows and 3 columns. So I'm going to do this over the third column. This column C sub 3. So according to the method of cofactors and minors, that determinant is just A sub 1, 3 times the cofactor A sub 1, 3 plus the matrix element A sub 2, 3 times the cofactor A sub 2, 3 plus A sub 3, 3 times the cofactor A sub 3, 3. So again, I have 3 terms. And so let's evaluate each one at a time. First one is A sub 1, 3. By inspection, that matrix element is just number 1, the number 1. So the cofactor A sub 1, 3 is minus 1 raised to the 1 plus 3 power times the minor m sub 1, 3. And once you start getting to the hang of doing these problems, you know, you can start going at a faster clip. The minor m sub 1, 3 is just the determinant of the matrix you get when you eliminate the first row and the third column of the original coefficient matrix. And that's just this determinant. And you can evaluate it using a rule from high school. And it's just minus 6. So my first term, A sub 1, 3 times the cofactor A sub 1, 3 is 1 times minus 6. So 1 down, 2 to go. The next term involves the coefficient A sub 2, 3. By inspection, that's just minus 1. So I have to evaluate this cofactor, A sub 2, 3. That is minus 1 to the 2 plus 3 power times the minor m sub 2, 3. Again, the minor m sub 2, 3 is what you get when you calculate the determinant of the matrix where the second row and the third column have been eliminated from the original coefficient matrix. So it's a matrix of smaller order. It's a matrix of order 2. And in fact, he looks like this. You can evaluate this determinant, and it's minus 2. Finally, our last term involves a matrix element A sub 3, 3, which is 1 by inspection. The minor, or rather the cofactor, A sub 3, 3, is just minus 1 to the 3 plus 3 power times the minor m sub 3, 3. And again, you develop some fluidity and expertise in knocking out these minors. But again, just go slowly because you can make an arithmetic mistake. 2 times 3 minus 1 times 0. So that's plus 6. So if you put all this together, by doing the expansion of the determinant of A about the third column of A, you have 3 terms, minus 6, minus 2, plus 6, and lo and behold, you get minus 2. It's the same result as before. So you will have ample practice on problem set 1 to in fact show that you have some expertise in using the method of cofactors and minors to calculate determinants. We actually did it 4 different ways. So this is not a rigorous proof, but what I'm getting you to perhaps realize is it doesn't matter over which row or column you do your expansion of the determinant in the method of cofactors and minors. So for this example of a 3 by 3 coefficient matrix, there are in fact 6 different ways to solve this problem. You have 3 columns and you have 3 rows. And we've done it for at least 3, I think we did it for maybe 4 cases actually. Okay, so let's summarize. So what's going on? So if we want to solve a system of linear equations simultaneously, Cramers Rule is the tool that we've developed. In developing and writing down Cramers Rule, we discovered determinants. Determinants are great for matrices of order 2 or matrices of order 3. If you have a problem which has 4 equations and 4 unknowns, Cramers Rule is going to give you the task of evaluating a determinant of order 4. It has 4 rows and 4 columns. And that is going to be a problem. For that matter, Cramers Rule will give you determinants And depending upon how complex the problem is, you can imagine having to evaluate determinants that are 10 by 10, 10 rows and 10 columns. So high school is not going to bail you out on that. I showed you last lecture that if you use the high school rule to evaluate the determinant of a 4x4 matrix, you get the wrong answer. So you do have a solution. You have a way of addressing this problem. It's a method of cofactors and minors. And you have in the problems that we have in lecture gone over some examples. The beautiful thing about the method of cofactors and minors is that it replaces the problem. In order to find a determinant of a coefficient matrix A, it replaces the problem for, let's say, where you have the general case of n rows and n columns. It reduces the problem to just looking at a system that has n minus rows and n minus row columns. So in the previous examples we've looked at, we had determinants that were of order 3, or matrices whose determinants were of order 3. And we reduced them using the method of cofactors and minors to the problem of just evaluating the determinants of matrices of order 2. Similarly, you can imagine a problem where you originally have a 4x4 matrix to deal with. You have to calculate its determinant. Well, cofactors and minors says, I can help you out. I can basically recast that in terms of evaluating determinants of matrices of order 3. I know how to do that. Problem is that if you look at a problem where A is a matrix of order 10, has 10 rows and 10 columns, the best that cofactors and minors can do, at least on the first run, is reduce the problem to a set of 9 by 9 matrices. Then you're going to have to calculate the determinant of a 9 by 9 matrix, which is not easy. So you have to apply cofactors and minors again to get 8 by 8, and you keep working all the way down to something reasonable, like 3 by 3. So the method of cofactors and minors will work, but it's going to be pretty laborious. It's going to involve a lot of work. Now, I should point out at this time, and maybe this idea came to your head in going through some of the examples, that Cramers Rule only works if you have a problem that has n equations and n unknowns. And all the examples we've done so far in problem set 1 and in lecture 1 fit under this category. You can imagine trying to solve a problem where you have m as in Mary equations and n as in Nelson unknowns. And there's no way in the world that Cramer's rule is going to help you with that problem. So we've got to do better. We need to do better. And the way we can do better in this problem, in this task of solving a set of linear equations simultaneously, is that we need to avoid determinants completely. And I can give you a nice little graph to show you that while determinants are a nice idea to work with for small matrices, the problem becomes much more complicated when the matrices get bigger. And they don't have to be real big. So let me show you what I'm talking about. So let's take the example of a 2 by 2 matrix. It's a matrix of order 2. Turns out that that matrix has 2 factorial, or 2 sets of products of matrix elements. And we've seen that before. So let's use this rule and scale this up. If you have a matrix of order 3, its determinant is going to have 6 terms. And we have seen that. And I actually asked you to go through the detailed algebra to prove what the determinant of a 3 by 3 matrix looks like in problem set 1. So if you go to a 4 by 4 matrix, N factorial gives you the number of products of matrix elements. And again, your high school rule fails you because your high school rule would tell you that there are 8 terms. Turns out there are 24 terms if you go through the trouble of doing all the algebra to calculate the determinant of a 4x4 matrix, which, I'm not going to have you do that. We did that for 3x3, and you saw how tedious and laborious that was, but instructive. So if you just scale this up just a little bit, a 5x5 matrix, 5 factorial is 120. So there are 120 terms in the determinant of a matrix of order 5. They're going to be products of matrix elements, but they will comprise a term, and there'll be 120 of these terms. A 10 by 10 matrix is not really that big, but if you use this analysis, it turns out that there will be 3,628,800 terms. And if you go to a slightly larger matrix, 30 by 30, which again, by modern computational science and engineering standards, is not a big matrix. It's going to have a number of terms that I'm not going to be able to write down here. And if you actually try to do this on a, let's say an iMac, which is not a big machine, it's not a supercomputer, it probably would take you about, 10 to the 7 years to actually write that out, using an iMac. So the moral of the story is that determinants are great if you're looking at small systems. So let's go beyond Cramers Rule. For all those reasons that we just pointed out, we need to go beyond Cramers Rule. And the key reason why we're doing that is we want to go beyond determinants if we're going to be able to solve large systems of equations, linear equations simultaneously. I may say lapse into calling these equations, but in this course that's understood to be a linear equation. None of the equations we're going to be dealing with in this course will be nonlinear. So here's something that you might not recognize to be true, but it turns out to be. Here are 2 equations and 2 unknowns. They're linear, but just because I can write these 2 equations doesn't automatically mean that they have a solution. So how do I know that? Well, if I take these 2 equations and graph them, so the x-axis will be x of 1, the y-axis x of 2. One of these equations will simply be just a line. Both of these are equations of lines. One will have a negative slope, first equation, and the second equation will have a positive slope, second equation. And the neat thing is that you see immediately these 2 equations intersect. They have a common set of points, x of 1 and x of 2, where they both have the same value. And you can calculate what that is. We've done this before. So for this particular case, case 1, there is a unique solution to my problem. And you can see where it comes from geometrically or graphically. It's just the intersection of these 2 lines. Okay, so let's extend this analysis and look at another case. Again, 2 equations, 2 unknowns. 2x of 1 plus x of 2 equals 3, and 2x of 1 plus x of 2, let's say that equals 5. These 2 equations you should immediately recognize are just equations of lines. So I can plot them in 2 dimensions. X-axis will be x of 1, y-axis will be x of 2. And it turns out that when you plot these 2 equations, and I invite you to do that, they both have negative slopes. They both look as follows. And in fact, what you will discover by just looking at these solutions, these 2 lines are parallel to each other. They never intersect. So no solution exists. Exists, plural. Need an S at the end of that. So no solution exists for this particular case. And graphically, you can see that in this figure. Those two parallel lines will never intersect. So it's a radically different scenario than case 1. How about a different case, case 3? Again, I'm just picking very simple systems so that I don't get involved in too complex a set of calculations to look at. So here's an equation, 2 times x of 1 plus x of 2 equals 3, and 4 times x of 1 plus 2 times x of 2 equals 6. Now, before I do anything, you should look at these two equations and see if you can come up with something remarkable about them. I'm not going to say anything further, but you should look at them. So let's go to the drill. The drill is, let us plot these two equations in 2 dimensions. And it turns out that the equation 1 will have a positive slope, and equation 2 also has a positive slope, and it coincides exactly on equation 1. So these two lines are on top of each other. They are superimposed. And that means that they don't have one solution. Since they lie on top of each other, there are an infinite number of points that will satisfy these two equations. So there are an infinite number of solutions. So in summary, for the simple example of 2 equations and 2 unknowns, there are 3 possible cases or scenarios. One case gives you a situation where there is a unique solution. The 2 lines intersect. The second case gives you a result where the lines are parallel, so no solution exists. And the third case gives you a result which tells you that there are infinite number of solutions. Namely, the 2 lines are superimposed on each other. So those are really the 3 results you can get. Those 3 possibilities are the only possibilities you can get when you actually sit down and try to solve a system of linear equations simultaneously. Okay, so we need to look at these 3 cases in more detail and figure out what's going on. And so we're going to look at, in some detail, a method that will allow us to solve a set of linear equations without dealing with determinants. And as throughout this course, there's always a theme that to see what's going on, it's very helpful just to look at small systems, 2 equations, 2 unknowns, 2 by 2 matrices, 3 by 3 matrices. You can worry about a billion by billion matrices later on, once you've seen what's going on for smaller systems. So imagine I have the example in case 1. So let me do the following. Let us first construct from this problem a coefficient matrix. Again, I'm trying to outline a scheme where I can solve these 2 equations simultaneously and avoid or eschew determinants entirely. Well, that's easy, right? You can always write down the coefficient matrix by inspection. That's what it is. Next, I'm going to define something called a constant matrix. And I'm going to use the symbol capital B for that. The constant matrix is just the matrix that contains the 8 matrix elements on the right-hand side of those two equations. And I'll use B because that's a convention. It's going to be very useful throughout this course. And it's just a 2x1 matrix. The next thing I'm going to do is create something called an augmented matrix. And the way we will know, or tell our audience that we're dealing with an augmented matrix, is I'll just take a vertical bar, and then B. I'm taking A and B and fusing them together, gluing them together. So if I do that, this is exactly what I get. Now, the beauty of an augmented matrix is it captures inside of it a lot of information. Buried inside here are two linear equations, 2x plus 1y equals 3, and 1 times x minus 3 times y equals minus 1. So an augmented matrix is really a shorthand way of writing down these two linear equations. Now, I said I want to avoid determinants. I can do that. There's a price I have to pay, but it turns out the price is relatively cheap. I have to introduce the idea of elementary row operations. And these elementary row operations are going to be easier to implement and certainly much easier to do on a computer than calculating determinants. So let us start out with our example of my augmented matrix for this problem. There's the first row, there's the second row, and let's just check this for a minute. That's minus 2. Yep. Okay, so there are 3 elementary row operations that we will define. And so let's talk about them as follows. First one is we can multiply any row by a non-zero constant. So for example, if you multiply the first row by the number 2, then my augmented matrix becomes 3, 2, 1. The first row gets changed. The second row is left alone. And again, this augmented matrix is just shorthand notation for the following 2 linear equations. 4 times x of 1 plus 2 times x of 2 equals 6, and x of 1 minus 3 times x of 2 equals 5. Note that these are different from the original equations you would get from the augmented matrix before you applied the elementary row operation. So I get a different set of equations, but the solution does not change. And I'll leave it to you to prove this. If you actually solve these 2 equations, you get the same solution that you would get if you were to solve this set of equations. So an elementary row operation gives you a new augmented matrix, but it does not change the underlying solution. Okay, the second elementary row operation that we want to define and illustrate is as follows. We can interchange any pair of rows. So again, starting with the same example, here's the augmented matrix for that problem we started out with. It's going to look as follows. And what I want to do is interchange, so I'll write this down over the arrow. I want to interchange row 1 and row 2. So that means my new matrix, after I apply the elementary row operation, that's kind of sloppy, so let's clean that up a bit. My new matrix is going to look like that for the first row and that for the second row. Again, augmented matrices are just wonderful ways of encapsulating information. The information is just a set of linear equations. It's a new set of linear equations. It differs from the original ones. So these are new, but again, and I leave it up to you to verify this, the solution does not change. So elementary row operations don't change the fundamental nature of the solution, or lack of solution, if you will, for the original linear equations you're dealing with. 2 down, 1 to go. There's one last elementary row operation that we need to define and illustrate it. And it is as follows. We can replace any row by the sum of the row and a constant times another row. A lot of words, but let's just see what's going on here. So we'll go back to our simple example. We've built an augmented matrix for a particular set of linear equations, 2 equations, 2 unknowns. First row looks like that. Second row looks like that. And this elementary row operation says the following. If I take a Xerox copy of row 1 and multiply it by the number 2, I can add that result to row 3 or row 2, there are only 2 rows in this problem, and get a new matrix. So let's see what that matrix is. So these elementary row operations here are defined going from left to right. I will take a Xerox copy of row 1. So that means that row 1 is not changed. I'm taking just a Xerox copy of it. I then multiply that Xerox copy by 2. So my Xerox copy becomes 4, 2, 6. Add that to row 2, and then row 2 becomes changed. Simply that. And this defines an elementary row operation. Why? Because buried inside this new augmented matrix is the following information. I get a new set of linear equations, but again, I ask you to show that even though these are new equations, new linear equations, the solution does not change. Okay, so you're going to get more familiarity with using these elementary row operations and a new approach to solving systems of linear equations. And that new approach is the Gauss-Jordan elimination method. So the key thing about the Gauss-Jordan elimination method is, I may just drop the term method and just say Gauss-Jordan elimination, is this allows you to avoid determinants, because that's what we want to do. That's the name of the game. Determinants are great creatures for systems of matrices involving order 2 or 3. They are a pain for larger systems. So what we'll do now is take our 5-minute break. You can stretch your legs and we'll resume at 2:50. Okay, so let us resume and write down or remind ourselves what we're trying to do. So we want to use the Gauss-Jordan elimination scheme to solve a set of linear equations without having to worry about determinants. So let's do it for a very simple system. Here are two linear equations. The unknowns are x1, x of 1, and x of 2. And I want to use the Gauss-Jordan elimination method to solve for x of 1 and x of 2 without determinants. Okay, so the approach is, I'll write it out in words and actually apply it, going through several examples. The approach is to construct the augmented matrix which is just A glued to B, and use the appropriate elementary row operations. And I've just defined what the 3 elementary row operations are to place my original augmented matrix in what's called reduced row echelon form. That sounds like a mouthful. So I think the easy way to figure out what's going on here is for me to show you by steps and examples. So I remind you, here's the original augmented matrix for this problem, which you can just write down by inspection. So the first step of the Gauss-Jordan elimination process is to take my original augmented matrix and turn the 1, 1 matrix element into 1. So I have to come up with the appropriate, this is a -2, sorry. I have to come up with the appropriate elementary row operations to in fact do that. So that's easy. You actually take row 1 and divide it by 2. And you'll get a new matrix. You get a new form of the augmented matrix where you've done exactly what you wanted to do. You've turned that 1, 1 element into 1. Okay, the next step in the Gauss-Jordan elimination scheme or approach is to take what you got from step 1 and now replace the 2, 1 matrix element by 0. Turn that into 0 somehow with some application of elementary row operations. So if you think about it, you want to add to that 1 a -1. because that'll turn it into 0. So what you'll do is you'll take a Xerox copy of row 1, multiply it by -1, and add that result to row 2. So you will get the first row, and there's nothing that is done to the first row because you just took a Xerox copy of it. The original form of row 1 is left alone. But if you took a Xerox copy of row 1, multiplied it by -1, and it added that result to row 2, you would get exactly what you're trying to obtain, where now that 2, 1 element is 0. Okay, step 3. Let's write down the result from step 1. Okay, in step 3, you want to turn this 2, 2 matrix element into 1. Okay. So how can you do that? Well, if you just take row 2 and multiply it by -2/7, then you will get a new augmented matrix, which simply looks like this. So we're changing the form of the augmented matrix for a reason we'll see in a minute, but we're not doing anything to the solution of the problem. We showed that previously. But we're starting to write this thing in terms of zeros and ones, because zeros and ones are easier to deal with than rational numbers. How about step 4? Well, step 4 of the Gauss-Jordan elimination method, you can see by just starting with the output from step 3, that is this. And what I want to do is turn the A⁻₁ 3 matrix element, first row, third column, I want to turn that into 0. So how do I do that? Well, think about it. If you take a Xerox copy of row 2 and you multiply it by -3/2 and then add that to row 1, you should check the arithmetic, but you'll get 1 - 1, 0. You will have turned the 1, 3 matrix element into 0. And row 2, nothing happens to it. It's left unaltered. We are almost home. There is a 5th and final step in this particular problem where you apply the Gauss-Jordan elimination method to it. Again, as input into step 5, you start out with the output of step 4. And what you want to do here is turn this matrix element, A⁻₁ 2, into 0. So there's an easy way to do that. Using an elementary row operation. Take a Xerox copy of row 2, add it to row 1. So row 2 is not changed at all, but row 1 becomes as follows. Okay, you are finished. For reasons that we'll see in a minute, this form of the augmented matrix is what we call reduced row echelon form. So I will define exactly what I mean by reduced row echelon form in a minute, but just take for granted my claim that this is now in reduced row echelon form. So what are the solutions to this problem? Well, the solutions I can get by looking at the reduced row echelon form of the problem and starting from the bottom up and reading out what this is telling me. This is telling me that 0 times x⁻₁ plus 1 times x⁻² equals 1. So I start from the bottom and I go up. And then at the top, I have 1 times x of 1 plus 0 times x of 2 equals 1. So I get, once I've written my original augmented matrix in reduced row echelon form, I get a corresponding set of algebraic equations. So what are they telling me? Well, the bottom equation simply tells me that x of 1 is 1, and the top equation tells me that x of 2 is 1. So in fact, if you go back to the original problem, what Gauss-Jordan elimination tells me is that there is a unique solution to this problem. And again, in this problem, as in every single exercise we do either in lecture or on the problem set, check this. Go back and take these 2 solutions and plug them into the original set of linear equations and show that they in fact solve the problem. So the method, so what is Gauss-Jordan elimination? The method is to take the original augmented matrix and recast it in reduced row echelon form, from which you can read out the solutions. So this is nice, but I never really told you what we mean by reduced row echelon form. How did I know to use those elementary row operations to get my final result? So I need to ask and answer the question, what do you mean when you say an augmented matrix is in reduced row echelon form? So I'm going to do this pretty formally. I'm just going to write these things down, and then I'm going to see how they work by examples. Okay, so, and I'm actually going to go refer to this example we just looked at. So if a row of my augmented matrix does not consist entirely of zeros, then the first non-zero number in the row is going to be a 1, the number 1. And we call this a leading 1. So let's see how this definition jives with what we just looked at in the previous problem. Previous problem, we claimed that this final result is in reduced row echelon form. So here's row 1, here's row 2. Clearly row 1 does not consist entirely of zeros. So the first non-zero number in this row has to be 1, or the leading number or matrix element is 1, and this is a leading 1. So this meets this criteria. The second row does not exist entirely of zeros. So the first non-zero number in this row has to be 1. That's called a leading 1. And so what we obtained in the previous example certainly meets this criteria. Okay. The second definition of reduced row echelon form is written as follows. In any two, let me clear this up a bit. In any two successive rows that do not consist entirely of zeros, the leading 1 in the lower row occurs farther to the right than the leading 1 in the higher row. So let's go back and look at our example. And where we claimed that this matrix, just rewriting it, we claim that this is in row echelon form, reduced row echelon form. So there's row 1 and row 2. So row 1 and row 2 are two successive rows that don't consist entirely of zeros, so that's okay. The leading row in the lower row has to be to the right of the leading row in the higher row. And we've done that. So this meets the definition of reduced row echelon form. Okay. Third characteristic of reduced row echelon form, each column that contains a leading 1 must have zeros everywhere else. So again, let's go back to our example. We claimed in the previous problem, this was an example of an augmented matrix written in reduced row echelon form. Here is column 1 and here's column 2. It's clear that column 1 has a leading 1 in it. And what the third criterion says is that every other matrix element in column 1 has to be 0. That checks out. Here's column 2. Column 2 has a leading 1 in it. So criteria 3 must tell us that every other matrix element in column 2 must be 0, and that checks out. Okay, finally, there is one fourth and final definition for reduced row echelon form, that if you have a situation where there are any rows that you discover after you do these elementary row operations that consist entirely that's sloppy, excuse me, entirely of zeros, then these rows, are grouped together at the bottom of the matrix, or augmented matrix. It really is an augmented matrix. So here's the example that we looked at previously. Again, we claim that for that problem, we've written the augmented matrix in reduced row echelon form. But if you look at row 1 and row 2, they don't consist entirely of zeros. So you really don't have to worry about this criteria. It doesn't apply in this particular example. You don't have a row that consists entirely of all zeros. And let's be a little bit more careful. Excuse me, let's get the matrix right. Okay. So, like everything in this course, we need to go through some examples and see how all this is going to work. And so let's do that. Let's use Gauss-Jordan elimination to solve this problem, where you have 3 equations and 3 unknowns, and I'll just write down the equations. And the unknowns are x of 1, x of 2, and x of 3, respectively. Okay. So the first thing I have to do is write down the augmented matrix for the problem. By inspection, that's just 1, 1, 1, minus 2 in the first row, 1, minus 1, 1, 2 in the second row, and minus 1, 1, minus 1, minus 2 in the third row. So I start out with my original augmented matrix, and what I need to do is come up with a set of elementary row operations that will allow us to recast this in terms of row echelon form. I want to write this so that the final answer is in reduced row echelon form. Okay, so in going through this example, we're going to remind ourselves what are the definitions of reduced row echelon form. First of all, the A11 matrix element has to be 1. So you're okay. You don't have to do anything there. The A21 matrix element has to be 0. Because this leading 1 in column 1 is here. So A21 and A31 have to be turned into zeros. So let's do that one step at a time. The way to do this is to take a Xerox copy of row 1, multiply it by minus 1, and add that to row 2. And you should get, note that row 1 is not changed. I just took a Xerox copy of it. I didn't do anything to row 1. But I took a Xerox copy of row 1, multiplied it by 1 minus 1, and added that to row 2. So I'm going to change row 2 by doing the arithmetic carefully. And this is what I get. Row 3 is not even in the ballgame. I didn't apply any elementary row operation to row 3. And I'm on the path to writing this augmented matrix in reduced row echelon form. So what's next? Well, I want to turn this guy into 0, because after all, I now have a column, C sub 1. It has a leading 1 here, so I want to turn A sub 2, 1 and A sub 3, 1 into zeros. That's on the road to a reduced row echelon form, no pun intended. So a simple way to do that is to take a Xerox copy of row 1 and add it to row 3. Again, I take a Xerox copy of row 1, so it doesn't change row 1. Row 2 is not in the game at all. I'm not applying any elementary row operations to it. And then when I take a Xerox copy of row 1 to row 3, I get my 0 that I want here in the 3, 1 position. And I get a 2 there, a 0 here, and a -4 there. So column 1 is all set. It has a leading 1 in it and zeros everywhere. So I'm good to go. Now, the next thing I have to recognize is I want to turn this guy into a 1. I have to because it's in the row underneath the first row, and I want to turn it into a leading 1, which is to the right of this guy. So how do I do that? Well, if I just take a Xerox copy of row 3 and add it to row 2, I get the following. Row 1 is left alone, and row 2 becomes 0, 0, 0, 0, and row 3, I took a Xerox copy of it, so its original form is left alone. Now, alert, alert. Row 2 consists entirely of zeros. So the definition of reduced row echelon form says that, oh, okay, I need to put that row in the bottom. So interchange row 2 and row 3. So I can do that. Row 1 is left alone. Row 2 becomes row 3, and row 3 becomes row 2. Okay. All right. So I now have a situation where I wanted to go back to this problem of turning this guy into 1. Remember, the leading 1 of the second row has to be to the right of the leading 1 of the first row. So there's an easy way to do that. I just divide row 2 by the number 2. And I get that. And again, row 3 consists of all zeros. It's at the bottom. The leading 1 in row 1 is there. The leading 1 in row 2 has to be to the right of the leading 1 in row 1, which it is. So I'm almost there. I mean, the key thing here is I'm replacing the original augmented matrix by essentially zeros and ones. So let's look at columns. If you go back and look at one of the criteria in the definition of reduced row echelon form, if you have a column and you have a leading 1, all the other matrix elements have to be 0. That's clearly true for column 1, and that's clearly true for column 3. It's not true for column 2. So my leading 1 is here in row 2, so I have to turn this A sub 1, 2 matrix element into 0. If I do that, I'm meeting one of the definitions of reduced row echelon form. Okay, so what's a way to do that? We'll take a Xerox copy of row 2, multiply it by -1, and add that result to R sub 1. And you should get a final result where you've changed row 1, row 2 is not changed. I just took a Xerox copy of it, and row 3 was never in the game at all. And if you go back and look at the definition of reduced row echelon form, I claim that this augmented matrix is now in reduced row echelon form. I've done what I've decided to do. Okay, so the answer is in there. I just have to tickle it to get the answer out. So I start from the bottom and work my way up to find the corresponding set of algebraic equations. And so what are they? Well, my first equation, I'm really worried about x sub 3. And it says that 0 times x sub 3 is in fact 0. My second equation is going to read x sub 2, starting from the bottom and going up, is minus 2. And my third and final equation says that x sub 1 plus x sub 3 is 0. So this is telling you something very important. What you have to do is be able to read what it's telling you. First equation, starting from the bottom and going up. First equation tells you that x sub 3 can be anything, namely any real number times 0 is always going to be 0. X sub 2 is pinned down to equaling minus 2. And I'll write this in red. X sub 1 is just minus x sub 3. So I'm not getting a unique solution in this problem. X sub 3 could be anything. It could be pi, it could be 1.73, it could be minus 13, it could be a billion. X sub 2 is fixed. X sub 1 is just minus x sub 3. So in fact, there is no unique solution to this problem. There's no value of x sub 1, x sub 2, and x sub 3 that you could cook up with that'll solve all three equations simultaneously. In fact, there are an infinite number of solutions, because you could pick, you have an infinite number of choices for x sub 3. So in a sense, this is a problem where there's not one pair of numbers, x1, x2, and x3. There are an infinite number of them. Now, you could have gotten this solution, well, you think you could have gotten the solution using Cramers rule. But if you go back and look at the original coefficient matrix for this problem and try to use Cramers rule, you'll discover that the determinant of that 3 by 3 matrix is 0. So Cramers rule is actually not going to help you at all. It fails. And so really, this is our first example, excuse me, of how Gauss-Jordan elimination picks up from where Cramers rule falls down. And Gauss-Jordan elimination solves this set of linear equations, these three linear equations simultaneously. The problem is that there's no unique solution. There are an infinite number of solutions. So remember the simpler case we looked at before, when you solve systems of linear equations, one of three things will happen. Either you'll get a unique solution, either you'll get no solution, or you'll get an infinite number of solutions. And that's what's happening here. Okay, so I maintain that to see how Gauss-Jordan elimination works, you need to go through examples. And that's the goal of problem set 2. And we'll look at another example now. And this is going to be a slightly different problem. Where I'm going to have 4 unknowns, x of 1, x of 2, x of 3, and x of 4. But I'm only going to have 3 equations. So this is a problem that Gauss could not even begin to think about. Because remember, I'm sorry, Cramer could not begin to think about, because Cramer's rule only applied to the situation where the number of equations equals the number of unknowns. So in this problem, you have 3 equations. You have 4 unknowns. And this is an example of a problem that's said to be underdetermined. You have more unknowns than you have equations. So that's not going to stop us. Let's just try to see what we can get using Gauss-Jordan elimination. So again, the setup is the same as before. You can discover and write down the coefficient matrix by inspection, and you can write down the constant matrix by inspection also. Again, no determinants at all. Next part of the Gauss-Jordan elimination method is to write down the augmented matrix. You have to do this carefully. There's the first row. Here's the second row. And here's the third row. Now, in using Gauss-Jordan elimination, you're going to have to come up with a set of elementary row operations to recast this in reduced row echelon form. So I'm introducing a abbreviation here. And in fact, there's a method to my madness. The reason why I'm using this abbreviation is this is the actual command in Python that allows you to find the reduced row echelon form of an augmented matrix. Now, I should say this. Your choice of an elementary row operation is up to you. But I will give you some guidelines of what you should do, so you're not doing hundreds and hundreds of operations. So for example, in this case here, the 1, 1 matrix element is 1. So you're okay, you're fine. So that'll be the leading 1 in column 1. So you want to turn this 2 into a 0. So you want to find an elementary row operation that does exactly that. I claim if you take a Xerox copy of row 1 and multiply it by -2 and add that to row 2, you will get the following. Row 2 is changed. So the good news is that you've turned this 2, 1 matrix element into 0. The bad news in quotes is that you've altered all the rest of these matrix elements in that row, but that's okay. The next thing you want to do is turn the 3, 1 matrix element into 0. Because that way, column 1 will have a leading 1 and all the other matrix elements will be 0. So what's the way to do that? Take a Xerox copy of row 1, multiply it by -4, and add that to row 3. And you will get row 1, that's not altered. Row 2 is not altered. But row 3 is altered. And we're a little sloppy, so let's clean this up a bit. So this is 1, 1, and this is -5, -5. Okay, So what I would like to do next is recognize that this leading one is to the right of this one, so that's okay. But I've got to turn everything else in column 2 into zeros. So one way to do that is to, let's see, take a Xerox copy of row 2, multiplied by -1, and add it to row 3. Row 1 is not changed. Row 2 is not changed because I just took a Xerox copy of it. And row 3 becomes that. So you can see where this is going. Let's look at column 1. It has a leading 1. Column 2 has a leading 1 here. Or let me say that differently. Row 1 has a leading 1. Row 2 has a leading 1. Row 3 does not have a leading 1. Well, there's an easy way to solve that. Take a Xerox copy of row 3, or take row 3 and multiply it by -1/5. I'll get this. So now all 3 rows have leading 1s. And now let's start from right and go to left. There's my leading 1. There's my leading 1. There's my leading 1. Starting over here, I have to get rid of this -4 and I have to get rid of this 5. I want all the other matrix elements in column 4 to be 0. So I can do that. This is an 8. So I can do that by taking 8, multiplying it by the Xerox copy row 3, and adding that to row 2. That gives me this. And again, I'm just trying to beat this into reduced row echelon form. This column 4 has a leading 1, but all the other matrix elements have to be 0. So I can do that by taking a Xerox copy of row 3, multiplying it by -5, and adding to that row 1. And I'll get the following. Row 1 looks like that. Row 2 will look like this. And row 3 will look like this. So I'm almost ready. Column 1 has a leading 1, and all the other matrix elements are 0. Column, I said 4, but I meant to say 5. Column 5, yeah, this is column 5, not 4. Column 5 has a leading 1, and all the other matrix elements are 0. So now I have to look at column 2 and recognize it has a leading 1. So I have to turn this 2 1 matrix elements into 0. That can be done by taking a Xerox copy of row 2, multiplying it by -1, and adding it to row 1. And I claim that I will get the following matrix. I will claim that this is now in reduced row echelon form. Should go back and look at the definition of that. reduced row echelon form. And again, that's just an abbreviation for reduced row echelon form. So what we're going to do next time in lecture 3 is that we're just going to study this to pull out solutions. And I leave it to you to, in fact, try it. Again, all you have to do is figure out what are the corresponding set of algebraic equations that this reduced row echelon form is telling you, starting from the bottom and going up. Okay, so next time we'll tackle this. We'll go through maybe 1 or 2 other examples of a Gauss-Jordan elimination. The method is much easier to employ than using determinants, as in Cramers Rule. Though we looked at a case where we couldn't use Cramers Rule at all because the determinant of the coefficient matrix vanished. You'll become more adept in recognizing what a reduced row echelon form looks like by going through examples. What you should not do is simply just use Python, plug in an augmented matrix and get the answer. Okay, that's not how to learn anything. That's like giving a second grader a calculator and said, I'm going to teach you arithmetic, punch in the numbers, and this is how you do addition, subtraction, multiplication, and division. So practice going over the examples we've talked about today. Look at problem set 2. That'll give you a good start into going through some examples. And again, it's okay to try to do a problem, and then you might get stuck. But go as far as you can, do as many of these examples as you can, and the solution key to problem set 2 will be available in a week or so. So next time we'll go through some more examples of Gaussian elimination, and we'll start talking about what one author has called the zoology of matrices. In other words, matrices are arrays that contain numbers, but it will turn out that there are special types of matrices that we need to identify, just as you identify creatures in a zoo. And we'll go through that exercise. Thanks very much.